Welcome to the Deep Dive. Today we're moving past some of the broader hype around large language models, and we're really getting surgical with a specific application, how modern transformer architectures are tackling and perhaps fundamentally changing the very challenging landscape of code-to-metric regression.
Yes, this is a deep dive right into a core bottleneck, really, in high-performance computing and machine learning generally. We're talking about predicting these hard, quantitative metrics, things like runtime latency, memory use, sometimes even model accuracy.
Directly from the code itself.
Directly from the source code, or maybe these complex computation graphs. And for decades, this prediction task has been agonizingly slow. It's been non-generalizable. Why? Because it demanded just monumental amounts of domain-specific feature engineering.
That feature engineering step, that's really the crux of the problem, isn't it? You're forced to manually craft these rigid fixed-length vectors.
Exactly. Counting specific operations, analyzing graph connectivity, running static analyzers. It's all manual effort just to feed data into a classic machine learning predictor.
But the research we're looking at today, it doesn't just improve that process. It feels like it sidesteps it almost completely.
It really does. Our focus today is squarely on regression language models, or RLMs. And the core idea, the proposition here, is that a single unified RLM can act as a general-purpose text-to-metric regression model.
Okay. General purpose across different domains.
Across profoundly diverse domains. We're talking about unifying prediction for, say, high-level languages like Python or C++A, and at the same time handling structural data like serialized neural architecture search graphs, all in one model.
So our mission today is, let's say, highly technical. We're really unpacking the methodology, the architecture, the quantitative results of this RLM approach. And we're assuming our audience, you are pretty fluent in ML, data science, the nuances of sequence modeling. The goal is a complete understanding of why this unified approach seems to be outperforming some very specialized domain-specific methods.
And the results really demand this kind of detailed look. I think the key finding right from the outset is the model's sheer generalization power. This work shows that a relatively modest 300 million parameter RLM,
which isn't huge by today's standards.
Not at all. Initialized using the backbone of T5 Gemma S, it achieves really superior performance across the board.
Okay, so give us some headline numbers. For high-level code, what are we seeing?
Well, for predicting dynamic peak memory usage in competitive programming solutions, that's the APPS dataset, they achieved a Spearman-rank correlation over 0.9.
0.9. That's exceptionally high for ranking correlation in this kind of task.
It really is.
Yeah.
And then if you pivot to the structural prediction side, the model shows remarkable transferability across 5 classic, highly complex neural architecture search design spaces.
These are the NAILS benchmarks.
Exactly. The unified RLM gets an average Kendall-Tau rank correlation of 0.461. Now, that number might not sound as high as the 0.9, but it's incredibly impactful because it means this generalized text model is competing head-to-head.
And sometimes winning.
And often outperforming state-of-the-art methods that were specifically built for graph structures, like dedicated graph neural networks or GNNs.
Okay, let's start by really defining the problem that the RLM was engineered to solve. You mentioned this fundamental constraint, the feature engineering bottleneck in computational graph regression. Why has this been such a persistent hurdle for so many years?
Well, the core issue, it boils down to fragility and a lack of transferability. Traditional methods, especially if you look at systems design, compiler optimization, maybe early NAS, they all rely on distilling this high-dimensional, often dynamic input, the code, the graph structure, into some static fixed-length vector.
Right, and that distillation requires manual feature definitions.
Precisely. Counting memory operations, calculating path statistics, maybe using graph kernels. You manually define what you think is important.
And the moment you make a system change, say, update the underlying hardware or the software primitives.
That fixed vector breaks. Imagine you're a compiler engineer. You update the instruction set, or you introduce a new kernel primitive, maybe even slightly modify a graph structure in a NAS space, add a new connection type.
Suddenly, your feature definition is obsolete.
Exactly. If your feature set relies on counting, say, 12 specific operations, and you introduce a 13th, your trained random forest, your MLP, it instantly loses context. The input dimension might change, or the meaning of the existing features shifts.
So the investment in building that feature set, building that model, is non-transferable. It's rigid.
It's incredibly rigid, it sounds like, and often is, a maintenance nightmare. You're forced to rebuild these specialized predictive models basically from scratch every time the underlying domain evolves even slightly.
Okay, so the RLM solution, by contrast, it kind of elegantly sidesteps this. It just treats the source code or the computational graph simply as a stream of text tokens, which aligns perfectly with the whole modern LLM paradigm, right?
It's a really elegant conceptual inversion, I think. Instead of forcing that complex graph structure into a fixed vector, you just let the pre-trained transformer encoder handle the variable length, minimally structured textual representation directly.
And the architecture leverages a pre-trained model.
Yes, it relies on the robustness of a pre-trained T5 Gemma S encoder. This processes the input text $6, whether it's Python code or an ONNX graph serialization, into this highly expressive, context-aware embedding.
And importantly, the mechanism used for regression itself is radically different. We're not talking about just sticking a linear regression head onto that embedding and predicting a single continuous value using mean squared error.
No, definitely not. RLMs fundamentally reframe regression. They treat it as a simple next token prediction problem.
Like generating language.
Exactly like generating language, but applied autoregressively over the numeric output value $. The model generates the number token by token, effectively treating the number itself as a sequence to be produced.
Okay, and that choice, that reframing, is what enables the universality you mentioned earlier.
That's the key enabler. Because if you look at the scope, the RLM demonstrates this across really massive modality leaps. The same unified model instance is tasked with predicting, say, the memory footprint of Python or C++ code.
Which is about high-level semantics data structures.
Right. Then, predicting the measured latency of specialized Triton GPU kernels running on specific hardware.
That's low-level hardware interaction.
Or reload level. And finally, predicting the accuracy and speed characteristics of complex neural network architectures represented as ONNX graphs.
Which is about graph structure and connectivity.
Exactly. And this joint capability handling abstract high-level programming semantics and concrete detailed hardware-software co-design graphs simultaneously in one model, that's really the definitive evidence. It shows the T5 encoder, just fed raw text, is learning some deeply meaningful abstract representation of computational cost and structure that actually transcends the surface-level domain.
Okay, so we've established the conceptual elegance, treat everything as text. But you mentioned the real sophistication. Maybe the reason this approach surpasses classic regression lies in how they handle that numeric output style numbers.
Yeah.
Let's dig into the RLM methodology, maybe starting with the architecture itself.
Right. So structuring the RLM as an encoder-decoder seems essential here. The encoder, as we said, leverages that T5 Gemma S pre-training to build a robust embedding of the input $6, the code, or the graph text.
And that pre-training is crucial because parsing code or graphs is complex. Starting from random would be much harder.
Much harder. Starting from random initialization, the model would first have to learn very basic token relationships, syntax, structure,
Right.
before it could even begin to map that structure to a predicted value.
And the paper's ablations confirm this directly. They show the value of inheriting that knowledge.
They do. Starting from the language pre-trained T5 Gemma checkpoint gives significantly faster convergence curves. And, importantly, superior final Spearman-rank correlations compared to an identical architecture initialized randomly.
So the model doesn't waste training time learning basic syntax.
It gets a head start. It immediately starts trying to relate the syntax and structure it already understands to the target metric, like resource consumption.
Okay, so that's the encoder. Now, shifting to the decoder side, you mentioned this key technical innovation, the normalization-free jaw representation using explicit digit tokenization.
Yes, this is, I think, a really major design departure from standard practice in regression.
Right, normally you'd normalize your target variable, predict a single float, calculate an MSE loss.
Exactly. But here, they tokenize the output number itself, digit by digit.
Can you walk us through how that works mechanically, like for a specific number?
Sure. So the numeric value tagger gets represented as a sequence of special tokens. These encode its components, the sign, positive or negative, the exponent, and then the mantissa digits.
So, like scientific notation, but tokenized.
Pretty much. Take a target value like 72.5. It's not fed or predicted as a single floating point number. It's tokenized into maybe, say, 8 or 9 distinct tokens. A token for positive sign, a token specifying the exponent, maybe like 101.1 or 102.2 depending on the scheme, and then individual tokens for 7, 2.5, and perhaps a special end of number token.
Okay, so if the target metric was very small, like $1 or 2 times 10^5.
Then the model's output sequence would start with a sign token, followed by a specific exponent token representing $10 and then the mantissa tokens, 1.2, and the termination token.
And the big advantage here is avoiding normalization.
Precisely. That's the core benefit. If you look across the datasets used in this paper, the target metrics span this huge dynamic range. We're talking microsecond latencies, maybe around 10 LRs, all the way up to large memory allocations, perhaps 105 bytes or more.
That's many orders of magnitude. Standard MSE regression would struggle with that scale difference.
Hugely. It demands meticulous, often dataset-specific, normalization, and scaling. Otherwise, your loss function gets completely dominated by the predictions for the large magnitude values, ignoring the errors on the small ones. Or you run into numerical stability issues.
And this tokenized approach means they don't have to pre-compute minimum or maximum bounds for $y on a per dataset basis. That sounds like a big practical win for a unified model.
It's an immense practical advantage. It simplifies the whole data pipeline. Plus, because the output is treated as a sequence of tokens, the model uses standard cross-entropy loss, just like in language modeling.
Which is generally more stable than MSE, especially with extreme numeric scales or potential outliers.
Generally, yes. And there's another crucial layer here. Constrained decoding.
Okay. So during inference, when the model is generating the number, it's not allowed to just output any random sequence of tokens.
Exactly. The decoder is restricted or constrained to ensure that the sequence of tokens it samples always forms a structurally valid number.
So for example, it couldn't predict 2 sign tokens in a row, or put an exponent token in the middle of the mantissa digits.
Precisely. If the model, maybe mid-generation, tries to output an exponent token immediately after it's already outputting mantissa digits, the constrained decoder would prevent that impossible sequence. It guarantees a syntactically valid number every single time.
Which prevents nonsensical predictions and adds reliability.
Absolutely essential for reliability. Now, moving beyond just predicting a single metric, this autoregressive decoder structure also offers a really superior way to handle multi-objective modeling compared to the traditional approach.
Okay, the traditional approach being attaching multiple separate dense heads to the encoder embedding, one head for latency, one for accuracy, etc.
Right. And the problem with that parallel head approach is the underlying assumption. It assumes that your prediction for latency, let's call it dollars, is conditionally independent of your prediction for accuracy, given the shared architecture embedding fear.
Which is often a flawed assumption in the real world, right? Latency and accuracy are usually correlated or constrained.
Fundamentally flawed for many system design tasks. A faster architecture is often smaller or simpler, which usually means lower accuracy. They're inherently linked.
So how does the RLM decoder handle this dependency?
Because it's autoregressive, it models these constraints naturally. Let's say we train the model to predict latency first, and then we chain the prediction, feeding the generated latency tokens as input for predicting accuracy dollars. The accuracy prediction, mathematically, point yx, becomes explicitly conditioned on the sequence of tokens representing the predicted latency dollars.
I see. So if the RLM predicts a very low latency for a given architecture, $6, it inherently knows, because of that conditioning, that the subsequent prediction for accuracy dollars is likely constrained to be lower too.
Exactly. It captures that hardware-software trade-off, that Pareto frontier concept, implicitly through the sequence generation process, without needing complex external modeling or multi-objective optimization frameworks baked in.
That seems like a major advantage, especially for tasks like NAS, where you're always balancing these competing objectives.
It really is. And finally, just to round out the methodology, the ability to train a single model on multiple quite disparate tasks, the multitask training aspect, is really a direct consequence of this universal textual input and output framework.
Right, because everything is just a string input and a tokenized number output sequence. You can just mix batches from, say, Python memory prediction and Triton latency prediction datasets.
It's trivial to integrate them. You just concatenate the datasets. This directly enables that crucial LLM paradigm, generalized pre-training on a massive mix of tasks, followed potentially by more specialized fine-tuning on a specific target domain.
Okay, to really appreciate what the RLM achieves, we need to understand the sheer diversity of the data domains they use for validation. The strength of a unified model is really tested by the variance of the data it can handle successfully. Let's start with the datasets focused on high-level programming language efficiency.
Right. The primary high-level set they used is APPS. This is a collection of almost 99,000 solutions drawn from competitive programming problems.
So real-world fairly complex Python code snippets.
Exactly. And the task is very specific. Predict the peak memory usage. They track it as dime-peak-colic bytes, which measures the memory consumed by the Python interpreter's heap at its maximum allocation point during execution.
And predicting memory complexity from arbitrary code like that is quite different from predicting latency, isn't it? Memory usage is often driven more by data structure choices, hidden runtime factors, not just raw instruction count.
Absolutely. It's a different kind of complexity. Then, the second crucial high-level dataset pushes the RLM much closer to hardware-software interaction. That's the Triton kernel latency dataset.
Triton being the language for writing GPU kernels within PyTorch.
Yes. This dataset has about 12,600 PyTorch programs that wrap around these low-level Triton GPU kernels. The RLM's job is to predict the actual measured execution latency of these compiled kernels when they're run on a specific GPU, an NVIDIA A6000 in this case.
So here, the model needs to analyze low-level optimization patterns, things inherent in the Triton language itself, which is explicitly designed for hardware acceleration.
It needs to understand how that Triton code translates to GPU performance. And the final high-level dataset, CodeNet, really introduces the challenge of multi-language generalization.
Across how many languages?
Across 37 different programming languages. CodeNet is enormous 7.3 million solutions that were marked as accepted on programming contest platforms. Here, the RLM is trained to predict memory metrics that were already recorded in the dataset.
Okay, but how does that work if it doesn't see the input program at evaluation time?
The crucial element here is how the train and test splits are structured. They contain submissions for the same underlying competitive programming problems. So the RLM isn't predicting an absolute metric in isolation from unseen code. Instead, it learns to contextualize performance within a problem set. It learns the typical performance profile of different algorithmic approaches to the same task across different languages.
I see. It's learning relative performance characteristics for known problems.
Exactly. Now, pivoting sharply away from abstract programming languages, we get to structural data regression. This is the domain of neural architecture search, or NAS. The input here is entirely different.
Right. We're not looking at Python or C++ text anymore. We're looking at graphs representing neural networks.
We are, and the critical choice the authors made for the input representation here was to use the Open Neural Network Exchange format, ONNX, specifically its intermediate representation, IR.
Which is a textual dump, but it describes the graph.
It's a textual serialization, yes, but it contains the complete auto-differentiation graph. All the operations, all the tensor shapes, the connectivity between nodes, it's all there in the text.
So the RLM just consumes this ONNX text. It looks structurally very different from Python code, obviously, but it still fundamentally adheres to that string input paradigm.
And that choice turns out to be highly effective for unification. ONNX is already the common interchange format used in ML compiler optimization pipelines.
So the RLM's predictions could potentially be plugged directly into those downstream tools.
That's the idea. And by focusing on ONNX, the model was able to cover something like 520,000 unique neural network architectures. These span nearly every major NAS search space you can think of. NASBench 101, NASBench 201, FBNet, various OFA families, MobileNet, Proxylus NAS, ResNet versions, the NDS benchmark suite. It's comprehensive.
And across all these diverse architectures, the single unified model has to jointly predict metrics like accuracy, FLOPs, parameter count, and latency.
Correct. Accuracy and various performance or cost metrics.
Wow. So that juxtaposition moving seamlessly from analyzing, say, Python data structure choices in the APPS dataset to analyzing complex graph convolution patterns in NASBench 201 ONNX files, that really feels like the ultimate stress test for the RLM's ability to learn generalized computational structure purely from text.
Oh.
Okay, let's transition into the quantitative evidence now. How well did this actually perform? Starting back with the high-level code results, you mentioned the APPS memory prediction performance was impressive, specifically in ranking solutions.
Yes, the Spearman-rank correlation, hitting 0.930 on predicting peak memory usage for APPS, is really exceptional. It's vital to remember, especially for this audience, in optimization tasks like program search or NAS, perfect absolute prediction isn't always the main goal.
Right. Often you just need to know which solutions are better than others. The relative ordering is key.
Exactly. A Spearman rank of 0.93 means you can very reliably identify, say, the top 1% or top 5% of memory-efficient solutions from a large pool of candidates without having to incur the immense cost of actually running and measuring every single one.
And the paper included some qualitative examples that really drive home the point that the RLM seems to be learning something deeper than just surface features, right? Like algorithmic complexity.
That's right. There's a nice example highlighted for a competitive programming problem called distance value. It involves comparing two different user submissions for the same problem.
Okay, what were the different approaches?
One was an efficient solution using extra space. It relied on simple scalar counters and straightforward linear loops. The second was a less efficient approach using no space. This one relied on creating large, intermediate hash structures, specifically using Python's counter object and set intersection operations.
So the overhead of building and querying those potentially large hash maps would dramatically increase memory consumption compared to simple counters.
Exactly. And the RLM picked up on this. It correctly predicted the memory usage for the efficient OO-based solution at roughly 5,488 bytes. But for the hash-based space solution, its prediction was almost double at 10,489.5 bytes.
That's fascinating. It demonstrates that the RLM's encoder, just by reading the Python text, is implicitly modeling the memory overhead associated with high-level data structure choices. It's quite a feat for a text-based model.
It really suggests a deep understanding of the code's implications. Now, turning to CodeNet, looking at the multi-language performance, the model maintained pretty respectable rank correlations across, I think it was 24 different programming languages analyzed in detail.
Which languages performed best? Was it predictable?
Well, C++ showed the strongest performance, reaching a Spearman-rank of 0.748. That's perhaps expected given C++'s more deterministic memory management compared to, say, Python. But the real surprise, I think, is the generalization capability.
Meaning good performance even on less common languages.
Yes, we see non-trivial rank correlations, values above 0.6, for quite complex and sometimes considered niche languages like Lua and even Haskell. This suggests the encoder is successfully identifying some general principles, maybe control flow patterns, data manipulation idioms that are inherent in the textual representation, regardless of the specific syntax or the underlying compilation target.
Okay, and connecting that back to the practical utility for something like program search, the ability to rank solutions within a single given problem is paramount, right?
Absolutely. The analysis showed that for over half of the APPS test problems, the RLM achieved a within-problem Spearman dollar greater than 0.54.
So in plain terms, what does that mean?
It means if you gave the RLM, say, 10 different candidate submissions, all trying to solve the same competitive programming problem, it was significantly better than just random selection at identifying the single best solution, the one with the lowest memory usage in this case.
Which has immediate applications in potentially finding optimal software implementations much faster than empirical testing would allow.
Definitely speeds up that search process.
Okay, let's shift now to the NAS domain. This is where the RLM faces maybe its toughest conceptual adversary, those specialized graph models we talked about. How does the RLM, using only a flat text serialization of the ONNX graph, actually compare against architectures explicitly designed to model graph connectivity, like GNNs?
Yeah, this is perhaps the most surprising result. You'd intuitively expect the GNNs to dominate here, but the data is quite clear. The RLM emerges as a frontrunner.
Okay, based on what metric?
Focusing on the Kendall-Tau rank correlation, which is standard in NAS literature, the RLM achieves an average tau of 0.461 across those 5 highly diverse NAS search spaces. Now, critically, this result slightly edges out the previous state-of-the-art method reported in some benchmarks, which was called FLAN dollars. That achieved 0.459.
And FLAN dollars often relied on extra information.
Yes, often it relied on incorporating so-called zero-cost proxies, which are essentially specialized pre-engineered features derived from the graph structure to achieve its strong results. The RLM achieves competitive or better results without needing these proxies.
Okay, I have to ask, how is this possible? Isn't this a bit of a failure for GNNs? They were purpose-built to handle graph topology and node connectivity.
Yeah.
How can a model reading a flat text file possibly capture that inherent topology better?
It's a really interesting question, and it suggests a couple of things. First, perhaps the existing GNN approaches struggle to generalize across very diverse graph families, or maybe they require too much architecture-specific tuning or large amounts of data per search space to truly capture the subtle structural patterns needed for performance prediction.
Okay, that's one possibility. What's the other?
The other, and perhaps more significant implication, is that the RLM's T5 Gemma encoder, particularly using its attention mechanisms, is proving highly effective at encoding the sequential and semantic relationships present within that ONNX IR text. It seems to learn to aggregate aggregate the contextual importance of neighboring nodes and operations described textually.
Effectively performing something like graph convolution, but through sequence attention on the text.
That seems to be what's happening, yes.
Yeah.
It's learning the graph structure implicitly from the textual description.
And the quantitative difference compared to some older but still dedicated graph methods is substantial.
Oh, absolutely. The RLM significantly outperforms techniques like Arch2Vec, which is essentially a graph autoencoder that scored only 0.212 tau, or Kate, which uses specialized transformers operating on token sequences derived from adjacency matrices that reached only 0.238 tau.
So the RLM proves that the textual encoding of the ONNX IR, when paired with a strong transformer encoder, actually captures the essential structural complexity needed for ranking better than these specialized graph processing pipelines did, at least in these benchmarks.
The evidence points strongly in that direction.
Okay, let's quickly revisit that multi-objective success on NASBench 201 you mentioned earlier. The RLM simultaneously predicting accuracy and 4 distinct hardware-specific latencies. This really showcases that conditional autoregressive decoder, right?
It's the perfect illustration of why modeling that conditional dependency is critical. Remember, the single RLM predicted the validation accuracy first, and then, sequentially, it predicted the latencies for 4 very different hardware targets: a mobile processor, Pixel 3, a specialized AI accelerator, Iris, a standard Intel CPU, and an NVIDIA GPU.
And when they visualized the joint predictions.
The density plots clearly showed that the RLM implicitly understood the inherent trade-off. Architectures that achieved higher predicted accuracy generally also incurred higher predicted latency across the different hardware. You could see the positive correlation, the slant, and the density plots.
It learned the Pareto frontier just from the data. And the accuracy of those specific hardware latency predictions was also very high, indicating practical utility for hardware co-design.
Extraordinarily high, particularly for the more standard platforms. The rank correlations for predicting Intel CPU latency reached a Spearman-rank of 0.960. For the NVIDIA GPU latency, it hit 0.939.
Wow.
This capability, a single model accurately predicting the performance implications of architectural choices across 4 distinct complex hardware targets, that's incredibly valuable. It could drastically streamline the optimization loop in compiler design and hardware-software co-design workflows.
Okay, so the performance results definitely confirm the RLM's effectiveness, but the ablation studies in the paper provide that crucial insight into why these specific design choices succeeded. Let's start with the central role of pre-training, both the general language pre-training and that interesting regression-specific pre-training idea.
Right. The benefit from language pre-training is pretty immediate and clearly confirmed in the results. Initializing the RLM from that existing T5 GEMMA checkpoint leads to significantly faster convergence, and crucially, a higher final Spearman RLM on complex tasks like the Triton kernel latency prediction compared to starting the same architecture from random weights.
So the generalized knowledge the model already has about language structure, token co-occurrence, grammar, that translates directly into a better starting point for understanding code syntax and graph structure descriptions.
It gives it a massive head start. And complementing that is this concept of regression pre-training, using cheaper, easier to compute synthetic metrics first.
Right. This seemed like a really neat idea for bootstrapping performance.
It is. The authors demonstrated that the RLM can learn to predict easy metrics almost perfectly. For example, predicting the floating point operations count, the FLOPS for a NAS architecture. They achieved an observed 1 mong own 1.99 line on that task.
And that's considered a cheap metric because it's deterministic. You could just calculate it directly from the graph definition.
Exactly. It's easy to calculate. So by training the RLM first on this synthetic, easy-to-learn task, they essentially teach the model how to trace the graph or count operations based purely on the textual representation.
It learns the basic mechanics of interpreting the graph structure from text.
Precisely. And then when they take this FLOPS pre-trained RLM and fine-tune it on the actual harder task, like predicting true measured accuracy or latency, which are non-deterministic and depend on complex factors, it accelerates convergence and also raises the final achieved Spearman error.
So it provides a kind of foundational skill. It teaches the model, okay, this text segment here represents a highly complex operation with many FLOPS. Once the RLM understands those deterministic rules of the graph structure,
it can more easily tackle the really complex, non-deterministic performance dynamics that are driven by subtle hardware specifics or training data interactions.
Okay, the second major ablation really confirms the necessity of that custom autoregressive output representation, the digit tokenization, compared to just using standard regression heads. The quantitative difference was substantial, wasn't it?
It really proves the weakness of relying on normalization when you're faced with extreme scale diversity in your target variables. On the NASBench 101 dataset, the normalization-free decoder head, using digit tokenization and cross-entropy loss, achieved a Spearman-rank of 0.800.
Okay, and the standard approach.
The standard normalized regression head, which required pre-calculating min-max bounds for the target variable, scaling the data between 0 and 1, and then applying MSE loss, performed substantially worse, only hitting 0.717 ARO-Hz. And crucially, if you tried to use an unnormalized regression head with MSE loss, it basically failed, dropping way down to 0.478 ARFers.
Right, because the loss would just explode or be dominated by the large values. So that large gap from 0.717 up to 0.870 really confirms that the custom explicit digit tokenization coupled with cross-entropy loss inherently manages those wildly different scales of values much more effectively.
Yeah, values ranging across 7 orders of magnitude in some cases. It handles it far better than traditional MSE heads that have this fragile dependence on pre-calculated normalization factors.
The cross-entropy loss just cares about predicting the correct sequence of digit tokens, not the absolute magnitude of the number itself.
Exactly, which makes it inherently more robust and much more suitable for a unified model that has to deal with metrics from totally different domains and scales all at once.
Okay, now let's look at the input side optimization. Specifically for that complex ONNX graph data, tokenization and sequence length seemed important there too.
They were. Given how dense and repetitive computational graph descriptions can be, standard large vocabulary LLM tokenizers like T5's default 32K vocabulary tokenizer are actually pretty inefficient.
Why is that?
Because they tend to break up common, meaningful operator strings like batch normalization or convolution 2D into multiple, less meaningful subtokens. So the authors trained a custom, much more compact, ONNX-aware sentence piece tokenizer. It had only an 8,000 token vocabulary.
And this custom tokenizer would learn to merge those frequent important operator strings into single tokens.
Exactly. It learns the common building blocks of ONNX graphs. And the practical benefit. It was dramatic.
How dramatic.
Using the default T5 tokenizer on NASBench 101 yielded a Spearman-rank of only 0.533. Just switching to the custom, smaller, learned tokenizer immediately boosted performance way up to $0.7232.
Wow, that's a huge jump just from changing the tokenizer. How does that work?
Well, merging those frequent operators into single tokens significantly reduces the total sequence length required to represent a given graph. The paper mentions, for example, that this custom tokenizer might reduce the sequence length by 30% on average.
Which means for a fixed context window limit in the encoder.
You can fit much more complex graphs, or roughly 40% more complex graphs, according to their estimate, within the same fixed 4,000 token context limit used by the T5 Gemma encoder. You're packing more meaningful graph structure into the same budget.
Okay, and building on that, they also showed that increasing the maximum sequence length itself provided further gains, confirming the model uses that global graph context.
Precisely. It wasn't a massive jump, but moving the maximum encoder context window from 1,000 tokens up to 4,000 tokens did increase the Spearman toger consistently, for instance, from 0.819 up to 0.838 on one task. It shows the model requires and actually utilizes that broader context to properly understand the complex, sometimes long-range dependencies within the serialized graph structure.
Okay, finally, let's touch on the resilience of this unified model structure.
Yeah.
And the nuances around fine-tuning it across these quite heterogeneous domains.
Right. The unified RLM demonstrated pretty strong resilience. They showed that jointly training the model simultaneously on both high-level Python code, like APPS, and highly structured NAS graphs, like ONNX, proved successful.
Meaning it didn't hurt performance on either domain. No catastrophic interference between the tasks.
Exactly. It managed to achieve the synthesis, learning effectively about both domains within the single model without performance degradation on either side compared to training specialized models.
That's impressive. However, the utility of doing subsequent fine-tuning seemed to depend heavily on the characteristics of the task you were fine-tuning on.
Yes, that's the critical trade-off, the nuance you need to remember. For tasks that were already very richly represented in the massive pre-training corpus, think about the high-resource languages within the huge CodeNet dataset.
Where the model had already seen millions of examples.
Mary, in those cases, trying to fine-tune the already well-trained RLM on just a small, specific dataset for that language actually did not help. In fact, it often caused performance degradation, a kind of catastrophic forgetting. The model over-optimized for the small fine-tuning set and lost some of its valuable generalized knowledge.
But the reverse was true for low-resource or perhaps out-of-domain tasks.
Absolutely. For NAS tasks like AmoebaNet or ENS, which were maybe minimally represented or absent in the initial large pre-training corpus, fine-tuning proved highly effective. Fine-tuning on just 1,000 target samples from those specific NAS spaces delivered enormous gains.
How large?
We're talking increases of up to plus multiple 0.35 in Spearman nanometers, huge jumps. This really confirms that the RLM's generalized pre-training creates an excellent starting point, a strong foundation that enables highly effective few-shot adaptation to new, potentially resource-scarce domains through targeted fine-tuning.
Okay, so to try and synthesize the central narrative of this deep dive, it really feels like regression language models have successfully challenged, maybe even overthrown, that decades-long reliance on rigid domain-specific feature engineering for code-to-metric regression.
We think that's fair. They demonstrate an ability to handle wildly diverse computational input formats, everything from human-written Python code to detailed compiling intermediate representations like ONNX, all within a single unified architecture.
And the foundational success seems to lie in two key ideas. First, treating all code and computational graphs universally as text sequences. And second, transforming the regression problem itself into a token-by-token, next-token prediction task, using that explicit digit tokenization.
Yes, that specific design choice for the output, coupled with the power of a strong pre-trained encoder like T5-GEMMA-S, allows the RLM to achieve surprisingly superior ranking accuracy, even when compared against highly specialized GNNs or traditional regression pipelines built for specific domains.
The immediate practical implications, especially for optimization tasks, seem profound. We could potentially significantly speed up program search,
Enable far more efficient hardware-software co-design iterations.
accelerate complex compiler optimization loops, where right now, getting rapid, accurate performance prediction is often the major bottleneck.
Absolutely. By sort of unifying computational graph regression into this generic sequence generation task, the whole engineering toolchain is radically simplified. You potentially no longer need separate teams, separate expertise, distinct modeling pipelines for analyzing high-level code versus predicting performance from architectural graphs.
A single RLM model, or variations thereof, could potentially cover a vast array of these predictive tasks.
That's the promise.
Which leaves us with that fascinating open question the authors pose for future exploration. Given that RLMs can accurately predict complex efficiency and performance metrics directly from structured code, how far can you push this generalization?
Right. If the model can accurately trace the downstream consequences of computational structure presented purely in a text format, the really provocative thought is, could these code-based RLMs be extended even further? Could they predict the numeric outcome of entire scientific experiments just by reading the raw experimental code that defines the simulation or analysis?
So analyzing the code itself, rather than needing to physically run the experiment or simulation, could potentially automate or accelerate parts of the scientific discovery process.
It suggests a potential future path, building directly on these findings. It's looking ahead towards maybe even full scientific discovery automation, driven by models that understand computation described as text, a fascinating direction to consider.